this becomes really complicated is if you build a heterogeneous stack that it's got, you know, a 3D game engine or a GUI library, you know, on top of a low-level API and on top of hardware, who's going to make sure that the pieces fit together? And this is kind of where I come in, or that's the sort of work that I like to do, is thinking about how do I make the pieces fit together really well. And so one of the places that I worked many years ago was Silicon Graphics, and one of the advantages that working at that workstation company was they did all of the pieces. They built hardware, they built software, they built all the pieces of the stack, and that gave the most opportunity to go make sure the pieces fit well together. Now, as we move into a world where a single company doesn't really supply all of the components, it gets harder and harder to make sure that the pieces fit together well. And so probably the best places to ensure that happens is the operating system vendors that have closed stacks like Apple or Microsoft. They at least can make sure that some of their layers fit together well, and they can have dialogues with hardware vendors to try to make sure that there's a good matching between what they're trying to expose in software and what's happening in hardware. For more open systems or having a bunch of disparate open APIs, it actually becomes really complicated to ensure that those different APIs fit together well. And so that's actually one reason that we have problems with having inefficiencies in the API, I think, is because there isn't anybody that's really overseeing and trying to make sure the pieces fit well together. And one of the reasons so I was at Microsoft for a while, and I did work on the overall stack. One of the reasons I came to Intel is that I'm sort of ping-ponging between the software side and the hardware side to try to get the pieces to fit better together. So another aspect that comes up all the time is what's the driver? How does it fit into this? And in this block diagram, I've drawn a line in there that separates where the programmer accessible entry points into the system are from the non-programmer points. But really, a driver is just another API. And what it's trying to do is it's the thinnest layer of abstraction around the hardware, and it's trying to provide a consistent view of what the hardware is to the lowest level API. And even the lowest level API in my model of the world isn't really trying to do much more than just provide a wrapper around the hardware that provides a set of hardware capabilities that are useful and provide the binding into the rest of the operating system, into the driver model for the operating system, those sorts of things. And so in the case of the driver, its purpose really is just to abstract the hardware. And it's the hardware vendor's responsibility for going and doing that abstraction. But there's an interesting dilemma in there in that the intent behind building a driver is that it's supposed to abstract implementation detail. And the importance of having that abstraction around implementation detail is to leave flexibility for doing alternate hardware implementations. But if a single driver model tries to span too many different disparate implementations, you get these inefficiencies. So I go back to that model of the world that says I have to have good matching between the different layers. If the driver is trying to provide something that's too general or hardware implementations underneath are trying to do things that are too widely varying, then I run into problems with efficiency of the system. And so one of the observations is that there really is this tension on the efficiency between the level of abstraction and what's going on in the underlying hardware. And this is a frequent comment that you hear from people working on programming and want to program at a low level is like, oh, the driver model's in the way or the low level API is in the way. But there is this complexity around trying to build something that is portable. So, for the rest of the talk, I've talked very generally about software stacks, but now I want to focus the rest of the talk on the graphics stack. And I'm going to use the graphics stack in the most general sense of graphics, meaning that it covers media and compute and all of the interesting uses that we have for the graphics hardware. But if I focus just on 3D rendering, that actually is a pretty good exemplar of what's going on. So the graphics stack example, again, at the top of the hierarchy, or the highest level of API abstraction, 3D game engine is an example. And that really is purpose specific towards focusing on things that I would need in a game engine or for implementing a game application. And that could include drawing the whole scene, focusing on how to build shadow maps and reflection maps and managing level of detail in the system. And less so about how do I draw individual lines and triangles and stuff like that. That's all in the lower level API. An example of that would be Microsoft's Direct 3D. And the interesting aspect about this is that the 3D API can be applicable to it just is the interface to hardware. So it's applicable to a much broader set of higher level APIs or higher level tasks. So I can use it to implement a graphical user interface, and in fact, in Microsoft Windows 7 and Windows 8, there is a layer that sits on top of Direct3D that is for doing graphical user interface. And then that sits on top of the driver layer, which is implementing this very thin abstraction to try to homogenize the hardware. And then, of course, the hardware is doing the mapping of APIs to hardware commands. Now, if you repeat this process for, say, 15 years or so, you get a pretty rich set of software modules or set of stacks that show up in the system. And so a few people at Intel were horrified when they saw this picture, mostly because of the colors. I actually drew this picture when I was at Microsoft 3 or 4 years ago. So when I wanted to learn Windows, to me as a software architect that cares about end-to-end, I have to understand all the components in the system and how they fit together and start organizing them in some kind of hierarchy that makes sense. And so this is the layers of abstraction going in the y-axis, and then in the x-axis it's for different purposes, like for example game engines or imaging or presentation, like doing PowerPoint or other Office applications. And really all I'm trying to show here is that the system actually gets complicated over time, and that really, for example, having a single bare metal API is not going to cause all these applications to show up easily in the ecosystem, that immediately more APIs will show up and stacks will get built to get leverage in the system. So this leads to a set of observations about software stacks. So the first one I just said is that vertical stacks really are necessary, that it isn't practical to have every application programmer trying to program to the metal. And then a consequence of this is that if the stack is successful, then it becomes really hard to replace it, because there's so much of the ecosystem or set of application programmers are making use of that stack. You can't really just throw in another one and say everybody should go port. Because of the way the stacks are structured, that they become more and more general as they work their way down towards the bottom of the stack. The lowest parts of the stack are actually the hardest to replace because they have the broadest use and therefore cause the most churn or most work for an application programmer to need to port. And so the best way to combat this, and again this is kind of a hard-won observation, is that evolution actually turns out to be better than revolution for supporting a mature ecosystem. That the best thing to do actually is not to just rip up and replace an API. It's better to figure out how to move that API forward and try to keep it efficient and add new features to it. And then that makes it more and more important to be able to design the API in such a way that it's easy to extend. And again, this is something that's not obvious if you first go design an API. That what do I need to do to think about being able to extend it into the future? Or what can I anticipate? What kind of features might need to be added? Do I even have an extension and versioning mechanism in the API so that an application can figure out what capabilities are there? Now, that isn't to say that there isn't room for new APIs. So another observation is that if a new API is added into the system, invariably it has to interoperate with the existing APIs in the system, that it can't be a standalone API. So an example of that would be, suppose I added a new compute or whatever API to the system. It'll need to operate with existing graphics APIs and be able to share data, easily and efficiently share data. If it only has its own version of buffers and surfaces or whatever the internal abstractions are, that'll almost ensure that it has very limited use in applications, because there will be a bunch of applications that are already using a bunch of existing APIs, and if I can't move data easily back and forth between the new API and the old APIs, I'm not going to bother as an application programmer using that new API. Okay, so the next thing I want to do is that kind of just set the framework for how stacks of APIs work together, and with a little bit of discussion about how graphics fits into it. Now I want to talk about where the interesting part about the APIs at the hardware-software boundary. And the way I'm going to do that is go through the historical evolution of the stack for the last few years. And the reason for doing that is I think it's instructive or informative to look at what had been done in the past and see if there are things that we could leverage, or also see if there are good ideas and see if there were ideas that didn't work so well that we want to stay away from. And graphics has actually been around for a long time. Going back at least to the 1960s, a little bit of work in the 50s. We don't have to go back and look at all of that, but probably looking over the last 15 or 20 years or so actually provides a lot of interesting information. So the way I'm going to look at this is again, looking at the example of the 3D graphics stack. I'm going to focus at the areas at the hardware-software boundary and the lowest level API. And what I want to look at is the system architecture. And I'm going to break it up into 3 groups, and I'm just going to give them labels. In the 1990s, I'm going to talk about what I call the workstation generation, with companies like Apollo, Hewlett-Packard, Sun, Silicon Graphics, the kinds of systems that they were building. And then in the 2000s, talk about the PC generation, what Microsoft was doing with DirectX and what Apple was doing. And then the final part I'm going to talk about is what we're trying to do now. And what I want to focus on is how did things work from an end-to-end or big picture point of view, and what aspects worked really well and what not so well, or where did things look like they started to go wrong. So the first one I'll talk about is this workstation generation. In this figure here, I'm showing an example of a system that I actually happened to work on, seems like a long time ago now. So this was back when graphics cards were this big and came in 3 or 4 that needed to plug into a VME bus or some complicated bus system, and there was maybe 20 or 30 ASICs on each board, and they're relatively complicated systems. This one actually, just to make the tie back to Intel, has a bunch of Intel i860s on it that were doing geometry processing. Anyway, what I want to talk about, what we learned from this generation is really the basic structure of the pipeline, of the 3D pipeline, and how fixed function fit in, and how to build an API that matched that pipeline well. And there was a whole bunch of history that happened before about, well, how do I even render a 3D primitive? Do I do it as triangles? Do I do it as trapezoids? Do I do it as higher order surfaces? I'm not going to talk about that. What I want to talk about is how did APIs fit into this, and what does the stack look like? And so those first pipelines, they really did simple things like transform vertices, assemble primitives, shape pixels, and do hidden surface elimination. And there wasn't any user or programmer exposed programmability, no pixel shaders or vertex shaders. But one of the things that we learned in building these systems was, for maximum performance and maximum flexibility, having what's called an immediate mode API was a good thing. And so an immediate mode API specifies how to draw, draw a particular primitive, for example, a triangle or a line or whatever, point by point or step by step. And it's contrasted with something like a declarative or retained mode API that really focuses on what to draw. So the difference would be in a declarative API, say, draw a red triangle. And so I said, draw red and draw a triangle, but I didn't actually say, lay down a vertex and lay down another vertex and lay down another vertex after that and set the color to red. And in the immediate mode API, that's what I would have done. And one observation is that it's relatively easy to build a declarative API on top of an immediate mode API. It's not possible to do the other way around. And so when I had that comment about how to build a good stack and talking about having good matching between the layers, this is why you want to have the low-level API be an immediate mode API. It's the most general mechanism for being able to manage the hardware. That isn't to say that there isn't a bunch of advantages to having declarative APIs and doing retained mode and stuff like that. This was an observation about how to get most flexibility. So then another aspect or learning that came out of the workstation generation was direct versus indirect rendering. And I'll show a picture to try to get the idea across here. So the contrast here is, what's the path between the application and the graphics hardware? How do I get maximum performance out of the system? And in the direct rendering model, it really is send graphics primitives directly to the hardware with no intermediaries. And I'll talk a little bit more in another picture or two about how that works. But the contrast for indirect rendering is to have something like another processor, another application service that sits between the applications, and it does demuxing. And so each application will talk to that rendering server, and then the rendering server will in turn send the commands onto the graphics hardware. And the difference there shows up in the driver model and the complexity in the graphics hardware about who does that demuxing. And that turns out to be a relatively complicated thing, but it's really expensive to have that intermediate body, that rendering service in the middle of things. And so most operating systems actually are bimodal, that they'll use rendering servers for graphical user interface or things where the performance demands aren't quite as high. And then for game applications or the really highest performance 3D applications, they'll do a direct rendering model of some sort or another. Now, how this gets implemented, this is, out of the workstation generation, we kind of got the 3-layer model of low-level API that does command translation and submission of commands to hardware, layered on top of a kernel driver, and the kernel driver typically does machine-wide resource management, so it's how I allocate textures, how I allocate render targets, how I control the display. It really is trying to make the graphics resource look like it's virtualized for each application, so each application sees its own private graphics device. And then the hardware layer really is doing the command execution and providing all of the memory resources and the execution resources. And so this is the example that I wanted to show for command submission about direct rendering. So back in the day when I was at Silicon Graphics, as an example, we would map a hardware resource directly into the address space of the application. And that would look like a hardware FIFO. And in order to send a vertex or to send a drawing command, it would essentially do a bunch of memory mapped writes. And the canonical example of sending a vertex to the graphics hardware looked like a jump from the application point of view, jump to the vertex command, 3 loads to load 3 floating point data, words to get X, Y, and Z, and then do 2 quad word stores and a return. And so that was it. That was all the overhead to talk to the graphics hardware. And I want you to keep that in mind, and we'll get to some later models and see how that changed. Now, one aspect that was interesting about this is that only one application could talk to the hardware at a time, and it was up to the kernel driver to do this demuxing that I mentioned, where it has to move the FIFO from one application to another on demand. And that's relatively complicated about how that's implemented. I'm not going to go into a lot of details here. Now, the typical way an API gets mapped onto this is try to do the simplest possible thing of build a command stream that either consists of 2 kinds of commands. Either it's something for setting some state, like what's the current color, or some attribute of the current lighting model, or what's the current texture to draw against, or some commands that actually do the drawing. So points, lines, triangles, all those sorts of things. And it works best if there's a one-to-one mapping between the API and the hardware. And so this was one advantage of trying to build this stuff end-to-end together in one company, is that you could build the hardware and the API and try to balance them so that it was a good compromise between what was expressed in the API and what's expressed in the hardware. And then places where things would always get complicated is around managing state. So that first set of commands for how to set the current color or current lighting or things like that, they become really complicated, and they need to be simple in order to make the API be efficient and not end up spending a lot of extra time in the CPU side, in the driver, trying to manage state. And an example would be, a really trivial example is 2 different states sharing the same register inside the hardware. That forces me typically to keep a copy of that register state in software inside the driver, and every time I update one version of the state or one side of the state, then I go update the entire register and send it to the hardware. Whereas if I had 2 separate registers, I don't actually need to keep a copy of the current state for the heart of what the API state is inside the driver. I can just immediately create a register write and send that off to the hardware. So another aspect of this is how does the resource management work inside? And the model is pretty simple back in the day, but it set a pattern of the graphics hardware typically has its own set of memory resources. You see these on the right-hand side, that the graphics hardware typically manages what I'll call the image-based resources, the memory frame buffers, the render targets, and texture memory, and then all the other application resources are in system memory. And that model is kind of stuck with us for quite a while. So now I want to contrast this with the PC generation. And again, don't get too attached to these labels. There's plenty of PC work that was going on, overlapping with the workstation generation. But the way I think about the PC generation is it added a lot of new features and a lot of new capability to the hardware pipeline. So that's where we got programmable vertex and pixel processing, and added a just-in-time compiler to the API in order to go generate code for those shaders on the fly. We also got a lot more sophisticated in terms of how do we render to texture, or making use of a lot more memory objects and doing multipass algorithms. And the hardware got modified to try to increase the flexibility for manipulating memory objects. And in DirectX 10, we were adding more logical pipeline stages. We added geometry shader. Then in DirectX 11, added the tessellator. And then it started to experiment with the compute APIs, and we get direct compute along with the X11 and OpenCL showing up from the open standards bodies. Now, to make things more complicated, we didn't just increase the feature set. We also added new challenges to the system because at this point laptops are becoming pretty important, and laptops add a couple different complexities. One is power management, that being able to open and close a laptop and not disturb an application. So the original PC model for using 3D hardware is, if you close the lid on the laptop and then reopen it, the application actually notices that it has to essentially reinitialize all its state. And that's not the best programming model for an application writer. And then we also start caring more about just dynamic display configuration. I need to plug in a projector and I'd like the projector to work when I plug it in, and we still struggle with that a little bit. And I spent a good chunk of working on Windows 7 trying to help improve the user experience when I plug in a projector, making sure that there is a pretty good chance that the screen would actually show up on the projector. And then security and robustness of the system, being able to deal with malicious software, being able to support content protection, becoming a bigger deal. There was a lot more hardware diversity, although I would say that kind of peaked in the late 90s and then it's waned since then. Chaz Boyd at Microsoft tells me that there used to be 40 hardware vendors that at sort of the peak of the Microsoft interactions, and then it got down to 4 or 5 in the late 2000s. And so that actually helped for removing some of the diversity. Now, one of the really big changes that's kind of highlighted by that slide that Sunil had that showed all of the different kinds of scenarios that are being supported, results in needing to be able to use the 3D APIs to do running multiple applications, doing different kinds of scenarios. That they're doing video decode, they're doing lots of different graphical user interfaces with lots of animation and fancy text rendering, and as well as being able to run 3D games. And really, on the PC side, the root of PC 3D hardware was all about running one single game at once, and there was a bunch of biases in the system or in the design to go simplify and make that as efficient as possible. That had to be undone in order to be able to support multiple applications. And so that includes being able to virtualize the hardware resource for each application and be able to deal with oversubscribed memory and be able to time slice the processing between different applications. And ideally also be able to isolate the applications from one another. So this is kind of the detailed picture of what's going on. And what I'm showing is 2 different versions of what the driver stack looks like. And I'll call this pre-Microsoft Vista and post-Microsoft Vista, where there was a big change in the driver model to support all the things many of the things that I said on that previous slide. So in the first model, and what I want you to do is compare this to the direct rendering case that I was talking about. So the application and the low-level API are building a stream of commands in a system memory buffer. When that buffer gets full, it gets passed on to the kernel mode driver. The kernel mode driver copies it into another buffer that is more amenable to being processed directly by the hardware. And then that buffer gets queued on a ring buffer and gets processed by the hardware. And so I made 2 copies, or I wrote commands to memory twice, and then posted a pointer to that buffer onto the ring in order to get things to the graphics hardware. And so compare that with the GL Vertex 3F scenario where I just wrote a few commands. Or so I wrote a few instructions to get something sent. Now, there's a bunch of differences in this because this is doing a whole batch of commands at once, but it's trying to do some amortization for doing more work in kernel mode. Now, there's some other interesting aspects that you can see. The dark green box, the shader compiler is sitting in the middle of the kernel mode driver, and from a architecture purist point of view, that just seems like a disaster. Why is this 3 million line compiler sitting in the middle of the kernel? Where the kernel is the thing that you want to be the most robust, and that you don't want to have errors in the implementation of the compiler where it blows up to cause the blue screen of death to show up on your system. So in the post-Vista world, a bunch of this got changed around within an application where the user mode driver was introduced, and much more of the code that was sitting inside the kernel got moved into user mode, and that reduces the likelihood of taking down the whole system. It narrows the set of components that can fail to a single application if there's some error in the user mode driver. And so the goal was to push a bunch up there. But it didn't really do anything about the efficiency of the system. In fact, it added a more complex kernel mode driver that is really trying to do this virtualization of the graphics hardware resources between multiple applications. I still need to go through 2 buffers before I can post stuff onto the graphics hardware and have it be executed. And the resource management model, it kind of stayed the same as the workstation model. No distinction anymore between render target resources and texture resources. Render to texture is such an important thing. Just think of it as image memory. And also, we can now put vertex data in that green box on the right-hand side. Now, in order to try to improve some scenarios as far as, is the CPU doing more reads or writes, or is the graphics hardware doing more reads or writes, it opened up this idea of also putting some resources on the system memory side. And this also introduces complexity for the guy writing the program to say, well, should this thing go, should I put it in system memory? Should I set a flag to put it in graphics memory? And invariably what we found is it's wrong half the time. And so the drivers end up putting code in to kind of reverse engineer what the application is really doing and setting the flags right. But this was an example of something that we tried to put in to improve performance. So going through before I get to what didn't work, let's talk about what does work. So this factoring between the low-level and API and the driver, actually, it's been a pretty good model, and it's allowed the hardware to change quite a bit. And when I say good model, I mean it's providing compatibility, that you can run these ancient applications on new operating systems, and they still work. And that isn't to say that that all came for free. The graphics hardware vendors that are building drivers like us, we end up having to do quite a bit of work to make sure that those applications keep running. But the point is the applications work. That I can change out the hardware, put new features in, and old applications that were using a more restricted set of features continue to work just fine. And so that we have supported significant hardware evolution in that time. We've gone through 10 years of evolution of features to PC graphics hardware. And we did one major reset, or Microsoft did one major reset in changes to the driver model to add this level of virtualization to allow multiple applications to make use of the graphics hardware. And then added additional versions to the API in terms of features like being able to add geometry shaders and tesselators and things like that. Now, the bad side is that there's still really large overhead in getting commands to go from the application through the API to the hardware. And one of the aspects that I pointed out a couple times was multiple memory writes and this driver transition from ring 3 to ring 0. And then there's latency and bandwidth constraints in moving the data because there are these 2 different memories, and there's I'll call it a skinny little bus connecting them together. So it might be a PCI Express bus, but it causes a complexity for how the programmer needs to think about things, and often data is being shifted from one side of the bus to another. If the application wants to manipulate data, it's best if it be in system memory. If the graphics hardware is manipulating the data, then it's best if it's in on the graphics hardware side. And often when I'm talking about this, I'm really thinking of the canonical discrete graphics card example. The things are a little bit different for chipset integrated graphics. I'm just not talking so much about that right now. I'll get there. So this has complicated the resource management and made it difficult for applications to pick. They have to understand their application so well and not guess wrong about where to locate their data. And this in turn gets reflected into API additions, and then the API gets more and more complicated. And the net result is that writing an efficient application, sophisticated application, gets more and more complicated to write. And then also the restrictions in the hardware makes it impossible to implement some scenarios. That if data needs to be moved back and forth quickly, or the latency in having command completion signaled and having the application go ahead and do something with it is too high. And an example of that might be being able to do occlusion queries in a 3D API. If if the latency in returning that result is too high, it just becomes too difficult to really make effective use of. So these things have been accumulating for a while, and often you'll hear cries from frustrated programmers saying, why can't we do something about these? So the question is, can we do something about them? And so cue the processor graphics generation. And that's the term that we're using for on-die integration of CPU and graphics. And really what we expect is that this to show up in all of the hardware, workstation, desktop, notebook, all the way down to phone, that it's just inevitable that all of the components become more and more integrated together, and that's the way to start thinking about the system. And so that's the thing that brings us to system on a chip, but I'm not going to talk so much about system on chip. I'll just talk about combining CPU graphics and memory controller together as processor graphics, and what are the opportunities, and usually with opportunities there's some challenges that come along as well, and can we start to fix some of these problems. So just again, to get the idea across, I work at a hardware company, I got to show a picture of a die. So this is Sandy Bridge. You can see the level of integration that we have the graphics processing on the left-hand side, and we have a shared cache that both the graphics can use and the CPU cores can make use of, and then it goes out to the memory system. And I'm sure you've heard lots about Sandy Bridge, and a little bit less about Ivy Bridge. But this is the model that we want to focus on. Now, drawing it as a more diagrammatically, the way I've been drawing those other pictures, the simplest way to think about this is by smudging the left-hand and right-hand sides together, where smudging would be the technical term. And so all I did was stick them together, and what we really want to do is talk about, well, what if we did more than just stick them together? Like, why keep the model exactly the same? Once they are together, is there something that I should do about it? And so what I want to do is talk about 3 different opportunities. And the way I think about these is integration is this opportunity to improve efficiency. So I can get higher bandwidths, lower latencies, and what I really like to get from a programmer's point of view is a simpler API if I can. And so we'll look at it as 3 classes of opportunities. One is around the data side, about improving the data access and efficiency. Another is about, can we do something about the amount of work that it takes to get commands or get work submitted into the graphics hardware. And then a third that I haven't really talked about at all is, is there some interesting aspect about power management that shows up in this? So first we'll talk about the more efficient data management. And so, at the bottom here in the picture, what I'm showing is the smudging, from the memory point of view, and the way I can think about this is, well, I got rid of that external bus. Now I can think about all of my graphics resources within my application. It could be in the same process address space, and then I should be able to have easy access to them because there isn't 2 different kinds of memory with different access characteristics. And what I'd like to do is make sure there's no gratuitous copying of data that's happening, or no redundant copies of data that needs to show up. And so that's the easy thing that we should be able to do. Let's think a little bit bigger. So the first thing to think about is, can I get rid of the memory allocation from the API? So, every OpenGL, Direct3D, they all have a create object of some type or another API, create vertex buffers, create textures, create render targets. What if I could just go ahead and create use the OS memory allocation routines like malloc or demalloc, depending on what OS it is, and go create my structures and just give it to the graphics hardware, and really think about it as something that's just managed by the application, that there isn't something where there's some inscrutable operations that's happening inside the graphics hardware or inside the graphics driver. And what would, one opportunity around that is to simplify the APIs enough around vertex buffers and index buffers, and that really is kind of getting back to the way things worked in the workstation generation. The original workstation generation didn't create separate buffers for it. All of the vertex and geometry data was in the application's address space, and typically they were part of application data structures that were used for other kinds of processing. Now the real trick is to go one step farther and be able to make the mapping of images, of render targets or textures into a cheap operation, make this mapping or locking operation where they're exposed to the CPU to be something very cheap. And I have this quote from John Carmack from about a month ago where he said, this is the feature I want to see most. And this one still gets a little bit complicated because it isn't just about having the CPU and the graphics processor in the same memory domain. There's also some questions about whether there's address or data layout transformations that are happening that make the graphics processing more expensive. Make the graphics processing cheaper, but make the CPU access more expensive. Whether it can comprehend, be successful with that's a little bit more of an open question. But just by unifying the memory and trying to have it all be in the same domain, same coherency domain, for example, it starts to open up the door for being able to do this. The next thing after that is can we do something about improving the submission efficiency for commands? And I've personally worked on a bunch of this stuff, and before we worked on the Direct3D 10 API and refactored the way the API worked to increase the amount of work per API call, and that was really trying to improve the efficiency, the amount of work that got done per unit amount of CPU instructions. Now with this being able to share memory and have memory in a coherent domain, can we get rid of this multiple copies of command buffers? And what we really want to do is write once, at best. And so when I make the API call, it immediately calls the driver, and the driver writes the hardware representation of the commands into memory, and I pass it on to the graphics hardware, and that's the end of it. But I got to be really careful about this because I don't want to compromise security or robustness of the system. That means that if I'm doing all of this creation of command buffers in user mode in Ring 3, I got to make sure that the hardware is capable of validating that it's correct, and I'm not doing something that'll compromise the security of the system. So from this perspective, I asked, can we get back to the kind of the workstation level of efficiency in that direct rendered model? And so the first thing is, can I just get to be writing to memory and then poke the graphics hardware in some relatively efficient way that doesn't involve going through kernel mode at all? And I don't have any specific announcement of we got it all figured out, but it seems like it's possible. Now the third part that I want to talk about is power sharing, or I'll use the term power sharing. So once we've integrated the components together in a single package, we can do some more interesting, I'll call it big picture power management, but it's big picture at the package level, and shift power between the CPU and graphics and other components. And so this diagram on the bottom of this plot is showing amount of power that's going to the CPU portion and to the graphics portion of the chip over time for an application. And you can see what happens is there are periods where the CPU has less demand, that there's not much going on that side, and periods where the graphics has less demand. And in those periods where there's less demand on one of the components, I can push power or allow the other component to operate at a higher power envelope that increases frequency and voltage. And that provides an opportunity to increase the throughput through the system. And the trick is, well, how do we do this? And Sandy Bridge is already doing this. Ivy Bridge is doing more of it. It's what's the basic underlying mechanism is that we need to monitor power and temperature and the amount of work going on in the system, and try to the real trick is to move it from a backward-looking operation where we saw how things were going and try to react to it, to trying to guess what's going to happen next. And what we want to do is have software that figures out what's going on and adjusts the voltage and frequency on demand for the two components in the system. And this might be one of these places where we go back and add APIs, and I'll be a little nervous about that because I said every time we add APIs to try to optimize the system, there's always the possibility that the programmers get them wrong and then the driver has to go reverse engineer what they're really trying to do. But it's something to go think about. And then of course, in turbo mode, we can actually take further advantage of this where we're looking at power lulls and taking advantage of accumulated thermal credit and boosting the overall frequency or power used by the system up higher than it normally could be until the chip heats up again. Now, a consequence of all this that programmers really need to start to think about is the importance of running lean CPU code, because now it's any wasted code that's happening on the CPU side, or for that matter on the graphics side, is wasted power that could have gone to the other side and gotten me more performance out of the system. And so this is kind of going to be a new way of thinking. So now kind of trying to talk about the big picture of where we could go. So one is we could look at changing the memory management model and use OS memory allocation. Another is that we could do some improvements in the command submission model. I actually don't think that necessarily requires changes to APIs to support, but it does need changes to the underlying driver model. things that might need to happen in the API is trying to support better asynchronous communication between the CPU and the graphics side. And there's another kind of programmer question about will they be comfortable and successful with doing that kind of asynchronous programming. The previous history indicates no, but maybe with enough education and experience we can get better at this. And then the one that I just mentioned is adding APIs to help with power management by giving hints or annotations in what's happening at various API calls. So to kind of summarize, what I've gone through is that, first is that the graphics API stack has evolved quite a bit, and I think that history is actually kind of interesting in terms of where we've been and what kinds of things have worked in the past. And we really should point out that it's worked remarkably well. It's like it is the best parallel processing system out there today. Like if you talk about doing parallel programming, the graphics system is the exemplar of success. It's been evolving and growing over the past 20 years and doing quite well. There's always room for opportunity. And so the question that we're asking, and we think the answer is yes, is there opportunities around processor graphics to improve these in the areas that we're looking at, our power management, this improving the command, transport, and efficiency, and the utilization and efficiency of data management in the system. And we think that we'll be tackling all of these over the processor graphics generation. Like this isn't hey, we fixed all this in Ivy Bridge. This is something that we'll do over the next several generations, but I wanted to give you some insight into where we thought it could go. And really the call to action at this point is, the processor graphics generation is upon us. And we need to as programmers and architects, try to figure out, how to take the best advantage of it. And the two examples that are showing up, just in Sandy Bridge is power interactions between the CPU and the graphics side and how to optimize for total system power, get maximum throughput through the system, and then how to take, best advantage of unified memory hierarchy. We've got this shared last level cache in the system. We've got this this unified shared memory between the graphics hardware and the CPU side. There's a lot of opportunity to get more efficiency out of that.